continue. Okay. Shall I introduce myself?
No, I'll start. So, okay, everybody, welcome to the next installment of the Non-Commutative Geometry Seminar here in Prague, remotely. The speaker this week is Shahn Majid from Queen Mary University of London, and he will speak about Poisson principal bundles.
Okay, thank you very much, Ray. It's a pleasure to speak in Prague, as it were. So for this audience, I'm going to keep it the quantum geometry part very brief. So I'll just give you an outline of the talk. Well, firstly, one will be recall quantum principal bundles. So I'm guessing, because this is one of Ray's favorite topics, that you've seen what this is in other of your seminars. So the version with general calculus. So okay, I'll say what that is. But the case of universal calculus you'll be familiar with as a Hopf-Galois extension. So I'll do that. So and elements of non-commutative geometry. But this is non-commutative geometry, not a la Con, but sort of a constructive quantum groups approach. And then I will semi-classicalize all the relevant notions. So a quantum group will be a Poisson-Lie group. So e.g. Poisson-Lie group. And then differential count. So this will correspond to a quantum group. Well, semi-classical version, obviously, that's Drinfeld. And differential calculus on an algebra, this will correspond to a contravariant connection. Navla-Hab. So that's obviously the algebra itself corresponds to a semi-classical level, corresponds to a Poisson bracket or a Poisson bivector. So I will explain that one, you know, I'll explain, and this one you probably know, and this one I'll explain. And then we will put this together to formulate the notion of a Poisson principal bundle. Okay, this is Poisson principal bundle. PLG is going to be Poisson-Lie group. Okay, maybe I should have written that. The definition. And then I will discuss associated bundles and connections, or connections on PPBs. So this would be infinitesimal notion of a quantum connection on a quantum principal bundle or its associated bundle. Okay, so that's the program. Okay, so part one. So part one, I will try to be very brief, just because I do think everybody knows this. So the model is A is like C infinity of M. This is the model. So it's an algebra, unital algebra. And what says that it's like a manifold is it has a differential structure, omega 1 A. I'll just say omega 1 for now. When there's more than one, I will put a subscript. So this is equipped. It's a differential structure at first order, means omega 1 and AA bimodule. And D is a map from A into omega 1, obeys the Leibniz rule. That's with respect to the bimodule structure, if you think about it. And the map A tensor A to omega 1, given by A tensor B goes to ADB, should be surjective. Now you can do without that condition, and then you will have you'll have something which is a bit weaker than a differential calculus in the usual sense. And then usually, there exists a non-unique extension to a differential graded algebra, omega D, with d squared equals 0, d obeys the graded Leibniz rule. Okay, so I'm hoping everybody has seen that. The other thing that everybody should know is what is a quantum group. So I won't say it. H is going to be a quantum group. So it's a unital algebra. I won't say all of it. And delta, just my notation, H into H tensor H coproduct. Epsilon H into the field per unit. And I'll use the Sweedler notation. Delta H is H1 tensor H2. There's a sum of terms. This is the most modern form of the compact Sweedler notation. Okay. S from H to H will be the antipode. Okay. Now, what do we need? We need omega on H. On H, omega 1. So this was omega 1 of H was the differential structure. Omega 1 of H, omega 1d, is left and right covariant. If so this is the coproduct viewed as a coaction on itself extends. So delta L of H dg is H1 G1 tensor H2 dg2, and delta R of H dg is H1 dg1 tensor H2 g2. If are well defined. So delta L goes from omega 1 into H tensor omega 1. And this should be a new page. I don't remember how I do that. Whoops, no, I don't want to do that. Page, new page after, right? Oh, okay. I don't know why it's done that, but I'm going to pretend that didn't happen. Okay, so that well defined, and in this case they become coactions. And in fact, okay. So that's when we say the calculus is covariant. So this is the analog of left and right translation can be compatible with a differential structure. Now a quantum principal bundle is an algebra P. Delta R from P tensor P tensor H coaction. It's an algebra Hom in this case. So that's a comodular algebra under a quantum group, Hopf algebra, with base A, which are the invariants. So, I mean, it isn't such that, well, then there's a condition and a further condition, which I will explain. So plus a transversality condition. If you know about Hopf-Galois extensions, that's where the Hopf-Galois condition would be. But I'm going to do it at the differential level. And so this is so in particular, we let omega 1p be a calculus, be H covariant. Okay, I technically haven't defined it, but the same idea as we had up there. The H covariant for the right coaction, and note that, and we let omega 1H be well, let lambda 1h contained in omega 1h be the left invariant forms of omega 1h. We assume that this is bicovariant. So it's both left and the right. And then we define a map Ver from omega 1p into p tensor lambda 1 by Ver pdq. I'll tell you what this all means geometrically later on. I mean, you probably know because we have to do it at the semi-classical level anyway. SQ1. Okay, I've got a compact notation for the a compact notation for the coaction as well, which was I'll say that in a second. D Q1 bar 2, where delta right of Q is Q0 bar into Q1 bar is the coaction compact notation. So now this, if you were to evaluate this against the dual of lambda 1, that would be like evaluating against the Lie algebra element. Lambda 1 is like the G star of a Lie algebra. And so evaluating with element of G would give you a map from lambda 1p to p, which would be a vector field. So this is the generator of the infinitesimal vector fields for the action of the Lie algebra classically. And that's where there's a kind of vertical direction. That's why we call it Ver. Okay. And we require, for the transversality, this condition, 0, p omega 1 AP goes to omega 1p, goes under Ver to p tensor lambda 1h. We've got this to be exact. And what this says is that these are the horizontal forms classically. So the horizontal forms, because this is the calculus. So omega 1a equals is contained in omega 1p. So the things that A generates, ADA, inside P, this is what it defines a calculus under our assumptions on A. So that's a calculus on the base. And this is the analog of horizontal forms. And that should be exactly the image of that should exactly be the kernel of Ver, the things that are killed by all the infinitesimal vector fields for the action. So that's the transversality. Okay, but that's all I'm going to say for now about quantum bundles. We'll come back to associated bundles and things like that later. Okay, so now let's do some elements of deformation theory. Maybe I'll start with deformation of well, I think everybody knows about Poisson Lie groups, so I'll just say the tiniest. You know what, I think I'll do that later. Let me do the deformation, since I'm here discussing differential structures. Let me remind you about, so now there's a formal way to do this, which is a formally formal star products would be defined on so C infinity of M, so A would be C infinity of M, and then formal power series in a parameter lambda, and then they would have some product of the form A star B would be a power series Ci of A B lambda to the I, where these are some differential operators, and this is the general framework. And we don't really care. We're only going to look at this to order lambda, but you can make this. You can say this very formally if you want and make it precise. Now the order lambda part, what you have is that that this minus the other way around. In other words, this is C1. Well, what this is is lambda AB plus order lambda squared. So the Poisson bracket AB, this is just C1 of AB minus C1 of BA. So we're just looking at the order lambda part of the deformation product. So you suppose there is a star product quantization of a Poisson bracket. Then you can recover the Poisson bracket like this. And notice that it's worth noticing that we don't really use, the fact that it's associative appears actually at order lambda squared. So we don't really know just from order lambda that this is a Poisson bracket. We just know that it's a bivector. So I should say associativity at O of lambda squared gives the Jacobi identity. Now, we're going to use the same philosophy for differential calculus. So suppose we have we'll start with a general vector bundle, a deformation of sections gamma of m of a bundle. So that means we're looking at gamma of m formal power series in lambda. We make a similar kind of product. I'm going to call the product bullet. And we have, and we look at a bullet dot eta minus eta bullet a. This is for eta in the original gamma of m. But we look at it, we look at the deformed product. So we suppose we've managed to quantize everything, all our data for differential calculus. And then we'll expand it like this. And there'll be some gadget here, which I'm going to call nabla dA eta plus O of lambda squared. Okay. Okay. So now what you discover is that nabla, this tells you that nabla hat A, looking at order lambda, zeta, is A nabla hat zeta. And nabla hat zeta of A eta is pi, this is the Poisson bivector, zeta dA eta plus A nabla hat zeta eta for all zeta in omega 1m. So this is this was an example of dA. A is a function on my manifold. So this is a covariant derivative, but not along vector fields, but along one forms. So such a gadget is called a contravariant connection. Or Lie-Reinhardt connection. So the references are in the paper, but this goes back to Heubschmann. I believe he was the first one to realize this in 1990, but many other authors have come to it since then, including myself in work with Edwin Beggs. So now, in the case of omega 1 of m, so we're looking at connections on omega 1 itself, we also have, coming out of the Leibniz rule, eta tor is nabla eta tor minus nabla tor eta for all eta tor in omega 1. So this is, I'm going to call this Poisson compatibility. Symplectic geometers might well call it torsion freeness, but I think that's confusing. Of a contravariant connection. Okay. So now just to explain, and this is the Schouten bracket, but just to explain where this is really coming from, you can equivalently write nabla hat dA to be nabla A hat. A hat is the Hamiltonian vector field along A. Generated by a function A. And then you see what this would really be saying is nabla a hat b eta is b nabla a hat eta plus a hat of b, which is otherwise known as the Poisson bracket of. So that's just like an ordinary connection. So it's literally an ordinary connection restricted to Hamiltonian vector fields. But it also obeys this, is a nabla b hat eta plus b nabla a hat eta, because Hamiltonian vector, so this is like a partially defined connection. So you find only along Hamiltonian vector fields, which means you can't multiply it via functions, but you can take their the product and then take their Hamiltonian vector field. That works fine, and so that behaves like a connection would obey. You can take the a and the b out, and then this other last condition, the Poisson compatibility, is that d of ab is nabla a hat db minus nabla b hat dA. So that was certainly how Edwin Beggs and I came to this. Now, but it's equivalent to a contravariant connection. Now, omega 1, a bimodule condition is a kind of associativity. So at O of lambda squared, that actually tells you that the curvature R nabla is 0. So it's actually a flat partially defined connection or a flat contravariant connection. We don't assume this. And that's because in non-commutative geometry, in the real world, there often does not exist omega 1 of classical dimensions, what we call a quantum anomaly for differential structures, preserving certain symmetries. So it's a very common situation that there are no-go theorems, and the simplest example is the quantum group SU2. So it doesn't have a bicovariant calculus of dimension 3. The smallest dimension calculus is 4-dimensional. And that corresponds to saying there is no bicovariant flat contravariant connection, bicovariant in the appropriate sense, on SU2. So I'm going to, that is flat. And so what that means is that when you quantize, even if they have a Poisson algebra and you quantize it to an associative algebra, but non-associative calculus. So this is one approach. It's and we can see it at order 1, and that's what we'll be doing. There is an alternative, which is to absorb the anomaly by extending the differential calculus. So you drop the condition of classical dimension and you allow a higher dimension, and then everything is fine. So in the literature, most of the time we do that. We extend the dimension, but if you want to do deformation theory, then you have to keep the dimensions the same, and then you have this anomaly and you're forced into non-associative calculus. So we're going to proceed, but we're just going to assume, and from a point of view of a geometer, you have a connection. It's not reasonable to assume that it's flat. There's no, unless you need to. So we don't need to. So we're going to proceed like that. Now, in the case of a Poisson-Lie group, so Poisson-Lie group, I'm going to be very, very brief. So this goes back to Drinfeld. So basically, it's just a group. It's a group with a Lie group with a Poisson bracket, and the map G cross G to G is a Poisson map in the obvious sense. Now, one thing I'm going to do is I'm going to define one of the things Drinfeld does essentially is to this Poisson bracket. I can always view it equivalently as well as a Poisson bivector, and I can view that equivalently as a function d from G into G tensor G, just by pulling it back. So I can write pi of G just as R G star D of G, right? So I can just refer everything back to the identity like that. And then one thing that certainly in most books on Poisson-Lie group theory, they look at this quantity, d by dt, t equals 0, of d of e to the t. So they differentiate d at the identity. And this gives you delta from G into G tends to G. And then what Drinfeld said is that if this is a Poisson Lie group, then this becomes a Lie bialgebra. And in the case of a connected, simply connected Lie group, it's the equivalent. So G delta Lie bialgebra. And before I proceed, I'm going to give you an alternative characterization. So lemma, this is in the paper. So G connected Lie group. This is a Poisson bracket. This is a PLG, Poisson Lie group, if and only if. And then we can write it like this: C acting on AB, and this means applying a left invariant vector field corresponding to the Lie algebra element C, should be the same as C acting on A, B, plus A, C acting on B, plus delta 1 C acting on A, delta 2 C acting on B. And here delta C is delta 1 C tends to delta 2 C, and there's a sum. Understood. Okay, so that's now the reason I've done it. So that's equivalent to a Poisson Lie group. It says that the Poisson bracket or the bivector is invariant under the infinitesimal action of the group, but not of the ordinary group. That would just be the first two terms. It's a Poisson Lie action because, well, it's not yet a Poisson Lie group, but it's defined with this extra term. And then and if you had a Hopf algebra, which was a deformation, if it had an enveloping quantum algebra type quantum group, the coproduct would be delta C would be C tensor 1 plus 1 tensor C plus the infinitesimal part of the coproduct deformation, which would exactly be delta C. So, you know, to order lambda. So this fits with your concept of a module of the deformation of UG being acting as a module algebra on the coordinate algebra. Okay, so that's sort of an equivalent way of capturing the content of a Poisson Lie group in a way that's good for us. Okay, so now with that in mind, I'm going to define. So I should have said something here. See, this guy here is just the action of the left invariant vector field. So this is just C tilde of A. So that's the left invariant vector field. So acting on A, it's C tilde of A. Here, C tilde of A at G is just d by dt A of G e to the t C. And I'm going to want to do it the other way. We also have similarly a right-handed version. A acted upon by C. I'm going to call it C accent like this, the graph of A. And it's just defined the same way. But this is just on the right. Okay, so the we're going to be working with a kind of bicovariant theory, so we will need it in both directions. So that's why I've done that. Now, to cut a long story short, the differential calculus on G. So a quantum differential calculus on a Poisson Lie group at order lambda. So that corresponds to a contravariant connection. Well, it has to have a certain form just by trivializing the cotangent bundle. So I'm going to write it. I'm going to write it in this form. Okay, nabla hat nabla tilde. Well, let me just write it first, and then I will explain. dA of S of G is going to be a Poisson bracket, sorry, with S of G plus C of G dA of G tilde S of G, where I've got to explain all the notation. So if I have, well, I'm going to identify omega 1 of G, I'm going to identify it with C infinity of G star, and I'm going to send a one form Tor is going to go to the one form Tor tilde of G, and this is just going to be LG star of Tor of G, similar to what we were doing. And so then I'm going to, so S is going to be in here. So I transfer, so nabla hat goes from omega 1, so nabla hat dA on omega 1 of G corresponds to what I called nabla tilde dA on C infinity of GS, of G. So I'm just using this to, and this should be a G star here, yeah, G star. I'm just, so using this identification, I'm going to just view my trochovariant connection direct as this map nabla tilde. Okay, like that. Here I take the one form and I view it back at the identity and back in G star. And here C of G blank blank goes from G star, tensor G star into G star. So these are Lie algebra slots for the dual of the Lie algebra slots. Okay, and so that's just I haven't said anything. I've just translated, sort of trivialized the bundle, translated my data into functions. And now this is, so proposition. This is translation covariant. So it corresponds to a translation covariant calculus, technically a left translation covariant calculus, in the sense, well, one, if you want. One, this is translation covariant, in the sense that it's the infinitesimal part of a left translation translation invariant quantum differential calculus, if you were to assume one, if and only if, and then the condition is that AB acted upon by C is A acted upon by C B plus A B acted upon by C plus A acted upon by delta 1 C B, no, sorry, I didn't say that right. That was just the Poisson, that's an equivalent formulation of the Poisson bracket. Forget that. Translation invariant, I meant the line below in my notes. Nabla hat eta Tor acted upon by C is nabla, I'll refer to the line I just crossed out in a second. Plus nabla hat eta Tor acted upon by C plus I delta C, I'm going to put a slope here, eta Tor acted upon by delta 1 C. Okay, if I finish this one here, this was going to be B acted upon by delta C2. So let me explain what I'm doing. So this notation of being a Poisson, the Poisson Lie group property here was done on the left. I could equally well have done it from the right. That would have been this one that I crossed out. And the notion of being left translation covariant is the same thing, but just applied to one forms. So it just ends up looking like this. And the dictionary that we want here, this was the tilde was the left invariant vector field. This is the right invariant vector field associated to an element of the Lie algebra. But otherwise, it's very similar. Okay, and this was a 2 here. Okay, so that's now. If you want, you can just take that as a definition, because if you don't care about all the deformation theory, and you can just take that as a definition of what you mean by a left translation covariant differential structure at order lambda. And but then, if you take that as a definition, then the non-trivial part is that this happens if and only if C is constant. What I call C, what I've called here C, is constant on G, i.e. given by some data C from G star tensor G star to G star. Okay, so that's characterization of Poisson left covariant differential structures, except we also need here, that was just the covariance part. Here, Poisson compatibility, if you like 3, Poisson compatibility corresponds to, and that's just a very simple condition, C of phi psi minus C of psi phi should be the Lie bracket phi psi on G star. So this is for all phi psi in G star. So a Poisson Lie group means you have a Lie bialgebra. The dual of the Lie bialgebra, the dual of delta gives you a Lie bracket on G star, and that should exactly be given by this. So that's our data. And then, so that was essentially, this is a revamp of an old result of mine with Edwin Beggs, with this covariance explained differently. But a genuinely new result is theorem. Nabla hat is bicovariant, so both left and right translation invariance. So this is the semi-classical version of a bicovariant differential calculus. If and only if, and there's a condition here. I'm going to write C star. So let me explain what I mean. C star of G of, so C star is a map from G into G tensor G. C star eta, I'm going to write as C star 1 eta tensor C star 2 eta. So then in this notation, eta C equals, so it's a very reasonable condition. It's eta C star eta commutator with C. This means two terms. First, it acts on the first part, and then it acts on the second part as the adjoint action on the right. Plus, okay, maybe I'll write that explicitly. 1 okay, plus delta 1 C tensor eta delta 2 C. Okay, so that's an equation that takes place in G. In G tensor G. So that's a Lie algebraic characterization of a bicovariant differential calculus. Okay. So now we need to move along a bit. So we're getting there. So we've understood what is the infinitesimal notion of the fiber of the fiber bundle. That is a Poisson Lie group equipped with a bicovariant differential calculus in the sense of a Poisson preconnection. A contravariant connection with this condition. Now, the next bit of data we need is we look at we can polarize these ideas. So instead of looking at a quantum group acting on itself, we can look at a quantum group acting on a space, or at the Poisson level. So we have a lemma. X a Poisson manifold. G a connected Poisson Lie group. Beta, a smooth right action. Of G. Is a PLG action if and only if. So it means that the map beta from X cross G to X is a Poisson map, but we give another characterization of it, if and only if C acting on PQ should be C acting on PQ plus P C acting on Q plus delta 1 C acting on P. So I don't need to prove this because it's just the same ideas as we had already. Delta 1 C acting on Q for all PQ in C infinity of X. And now the other, so that's polarizing what we did before in terms of the characterization of a covariant action. And we also need the analog of the left invariant vector fields will be C tilde of X will be beta X star of C. So this will be the infinitesimal vector field for the action of C acting on P for the action. And at the Lie algebra level, the Lie algebra will then act by these vector fields. And then we also have, we map Ver from omega 1 of X to C infinity of X tensor G, which just captures, if you just leave C to be blank, then it lives in G star. So it just captures this tilde construction. So here, identity tensor C on Ver would be interior product along C tilde. So this is the infinitesimal analog of the map Ver in the quantum case. Okay. And now we equip X now with a differential calculus, so with nabla hat on X, which is PLG covariant. And so now we just take the formula we had before, but the reason I wrote them that way was we can now polarize it, or which is just this one. So it's literally, this looks the same as the one we've already written. But now things just live in the more general spaces. I'll say where they live. Plus I delta 1 C tilde of eta, and then delta 2 C acting on tau. Now here, tau is in omega 1 of X. Eta is in omega 1 of G. Is in omega 1 X also. It's a differential calculus on X. And yeah, I don't know if somebody has a question. You're going to have to shout if you have a question. C acts on X. Well, C is in the Lie algebra. These I already defined. It's this map here, and this is the Lie derivative along delta 2C. That's in the Lie algebra, the vector field. So it extends. This action extends to one forms by the Lie derivative. Okay. So that's the appropriate condition. So this again looks like this is it's kind of transparent to somebody who's very familiar with quantum groups. It's like a modular algebra construction. Okay, so that's the data we need. So now I'm ready to define a Poisson principal bundle. Okay, so now suppose X to X mod G is a Poisson is a principal bundle first. Ordinary, it's a classical principal bundle. Okay. So let me remind you that if I call this space, I call this M. We've got omega 1 of M sits inside the horizontal forms, omega 1 horizontal, which sits inside the omega 1 of X. This is a sub-bimodule, or a sub-bundle, if you like, module. And so this is these are just the one form that's pulled back from the base, but as a module over C infinity of X. And these are the invariant, from here to here is a subset, and these are the invariant subset. So the G invariant subset. And these are characterized by here eta such that I C tilde of eta is 0. So they kill, so I told you that's a transversality condition for a classical bundle. So we suppose that we have a classical bundle. Then we define a Poisson principal bundle so PBB is a classical bundle principal bundle X over XG with 1 X Poisson. G is a PLG. The action X on X as a PLG action. It respects the Poisson structure the way I explained, as well as acting directly on X as a PLG action. 2, we have a bicovariant nabla hat G. So there's a bicovariant differential structure on G, which is Poisson compatible. So corresponding to some map C from G star tensor G star to G star. 3, there's a connection nabla hat X, which is differential calculus on X. This is Poisson compatible and PLG covariant. As I just explained. So as above. And then the last thing is the transversality condition, the extension of the transversality. The transversality at order lambda. And that is that I C tilde of nabla hat X eta tor is I C star 1 tilde of eta, I C star 2 tilde of tor, plus the Poisson vector bivector on X evaluated on eta and on D of I C tilde of tor. Okay, so that all makes sense, right? This gives you a function on X. This is now one form. You can evaluate it on the Poisson bivector. So this is all, this is the definition. Now, of course, we have to have a few theorems, which is what I have time for in the remaining part of the talk. which show that this all is kind of a nice self-contained theory. So, I mean, everything is well defined at the Poisson level, and you have to take my word for it, but if you had a quantum principal bundle and you make a deformation analysis and you see what you get, then you will get all this at order lambda. What are the first properties of these Poisson principal bundles? So here's a small result. In this case, M, which is X mod G, becomes a Poisson manifold with a Poisson compatible nabla hat M. So this is given by restriction. Just as we restricted the calculus on P to get one on A, nabla hat X. So these conditions ensure that this gives you a well-defined Poisson compatible connection. So the way I'm thinking of it is that an ordinary Poisson manifold is a manifold equipped with a Poisson structure, but a semi-classical Poisson manifold is a Poisson manifold equipped with a semi-classical part of the quantum differential calculus. So that's what you should really call a Poisson manifold. I mean, if you want to include the differential structure at the semi-classical level. So it's really the pair. I'm thinking of the pair of a Poisson, well, the triple, a manifold, a Poisson bracket, and a Poisson compatible connection. It's like an infinitesimal data of a quantum manifold. Okay, so now you can apply all of this, and I've got time to give you a little example. So you can apply all this to the hot vibration. So this is, I won't go into any details, but here CQS2 is CQSU2 invariant under CQU1. This is the algebraic circle, but the Q is in the differential structure in omega 1 so it's in the Q doesn't enter into the algebra. The algebra is just CTT inverse, but it enters into the differential structure. And this has its 3D calculus. So this has a Q-deformed calculus. This is dTt is QT dt for the algebraic circle. Okay, so then we can, this at the end of, I won't go through all the calculation, but at the end of the day, this gives you in complex coordinates, so x, z, z star, with z star z is x into 1 minus x. So that's a sphere, but just in the way it comes out in complex coordinates. You get Poisson bracket. And I'll just give you, not too complicated to write out, S2. This is xz, z star x minus xz star, and zx star, zz star is S2 is 2z star zx. If you want, it's like x squared 1 minus x squared. And but there's, so that's nice. We get so now let me just say that if you quantize, this is a sphere. If you quantize the usual sphere with the good quantization, so that's just the Kirillov constant bracket quantized as the enveloping algebra of SU2, then you get an SU2 invariant Poisson bracket. But this is not SU2 invariant. This is the infinitesimal part of quantum SU2 invariant. So it's it's the Poisson Lie group SU2 invariant, which is why it's not the Kirillov constant bracket. Nabla hat on S2, I won't just tell you one of them. DZ is DZ on DZ is 2x minus 1 z dz minus 2 z squared dx, etc. So you can compute everything. So just to illustrate how this works. Okay, So now I want to have the last section on connections on Poisson principal bundles. So let me remind you a little bit about the quantum level. So for a principal bundle, a spin connection, a connection if you like, in a concrete manner, is omega from lambda 1h into omega 1p. I defined all these things earlier, such that it's equivariant. This carries a natural adjoint coaction. This is the given coaction extended to differentials. Equivariant, and it undoes the map Ver. So omega of v should be 1/10 of v for all v in lambda 1h. Okay, so that if you think about it, that is the usual notion, just written in an algebraic way. And this corresponds to a projection, an equivariant splitting of omega 1p. And this is going to be given by the coaction omega, and I've just got to explain one bit of notation. And here, omega bar is from, this is the Moré-Cartan form on a Hopf algebra, on a group, on a Hopf algebra. Namely, omega bar of h is just sh1 dh2, and pi epsilon is just the projection from h into h plus, the augmentation ideal. It's just subtract. It's h minus 1 times epsilon of h. This is the co-unit projection. So this lives in, and I should have mentioned that omega 1h can be identified, is a quotient, is isomorphic to h plus modulo some relations. So it's a quotient of h plus, so this all makes sense. Okay, so that's an explicit construction. And we require to be strong. So there's so abstractly, pi omega is an equivariant splitting of omega 1p. I haven't got time for all that. But we do require omega 1 to be strong. And what that says is that identity minus pi omega dp should be contained in omega 1 ap for all p in p. Okay, so this is somewhat buried in my original paper with Brzezinski, but the result was, particularly this term was coined by Piotr Hayat, I believe. So this is Nabla 1. Now, what this gives us in this situation is what I'm going to call is a new approach, which is in my recent book with Edwin Beggs on quantum Riemannian geometry, which in chapter 5, which is we focus on this gadget here. So omega 1, I'm actually going to map it into omega 1p. This is a subspace inside omega 1p, but it's canonically identified with, I'll just say equals, omega 1a tensor over a p, just by multiplying, going in this direction, just multiply. And so that is actually a connection on p. So it's a kind of universal connection, equivalent to writing down omega. And this is explicitly, it's nabla p is dp minus, and then you apply this projection. So it's p0 omega bar pi epsilon p1. Okay, so, and in fact, it's a lemma. So this is chapter 5 of the book. I don't know if you know, but there is a new book that's out by Edwin Beggs and myself on quantum Riemannian geometry, so it's in there. This is the bimodule connection, nabla p. If I'll remind you what that means in a second, that if and only if ai omega of lambda 1h bi is 0 for all ai bi is 0 and ai d bi equals 0. So these are the things which would be 0 in if you started in the universal calculus and viewed them in the quotient and you got 0, then we should get this should be 0. Now I just need to remind you that a bimodule connection, in fact, I think given the yeah, I think I've got time. So so I'm assuming that people have some idea what is a connection. So I'll do a little aside since I didn't cover this earlier. On an A bimodule, E, so that's like a vector bundle, but from two sides. So a left one is, well, it's nabla from P, from E into omega 1 A tensor over AE. That's a connection. These are not contravariant connections, these are the actual honest connections. That's why I haven't put a hat on them. And I just see, I think about how much I need to say to you really. I think I'm just going to say the bare minimum. There's the Leibniz rule, obviously. So nabla of nabla, let me say nabla E. Nabla E of AE should obviously be dA tensor E plus A nabla E. But on the right-hand side, we also want from the other side. So EA, so this side is obvious, that's a usual left connection. And if you haven't seen connections before, if you were to evaluate against the vector field, you would have a map from E to E. So that would be the covariant derivative. So it's just a natural way that we do connections in mathematical geometry. Then this should be nabla EA plus sigma E tensor over A dA, where sigma E is a map from omega 1 A, or E tensor omega 1 to omega 1 A tensor over A E, bimodule map. Now, this data is not additional data. It's so this notion goes back to Dubois-Violette and Peter Michel. It's a very nice way of capturing the fact that we have not only a left Leibniz rule, but also a right Leibniz rule. But this is not additional data because it's defined by this equation if it exists. So it's just that some connections are compatible with the right-hand Leibniz rule as well as the left-hand one. And so those are the ones of interest throughout the book with Beggs. Okay, so that's the kind of data we want. So we're going to assume this in our case. And now associated bundles, if V is a right H comodule, we get associated bundle E, which is just P tensor VH, the invariance under the covariance under H. This is the associated bundle. But you also get an invariant connection, nabla E, P tensor VH, right, that's E, goes to omega 1 AP tensor VH, which is identified with omega 1 A tensor over AE. So these are all canonical identifications. And what this map nabla E is just nabla P tensor identity. So that's why I called nabla P the kind of universal one. And once you have nabla P, it induces a nabla E in a trivial way on all the associated bundles. So that's I think a neat point of view. Now, the last thing I want to do is, now the question is, how does this all deformation quantize? And you have a bit of a nightmare with that at first, because how are you going to deformation quantize the tensor product over a deformed algebra? That's going to take a huge amount of analysis, okay? So the secret to this is that we can cast, so to deformation quantize, so to construct a version of this we can cast nabla p. It just goes from p into omega 1 AP, sitting inside omega 1 p. So we only need to deformation quantize the total space, which we've already been doing. So we don't need to worry about tensor products. This doesn't mention tensor products anymore. And similarly, I've run out of time. So similarly, nabla, this goes from p omega 1a into omega 1 AP. So these are subspaces inside omega 1 p. And they'll be characterized by certain properties, and which we can just write down. So for example, nabla p of a b of p of a p should be dA dot p plus a dot nabla p p, but also from the other side, nabla p p dot a should be nabla p p little p times a plus sigma p p dot dA. My point is that these all make sense just inside omega 1 p. So we only have to view a quantization, and we never have to, of the algebra, we never have to mention any tensor products over A. And this induces, and this is actually sufficient, if it's covariant, then this will induce a covariant derivative on nabla on E as well. So I won't go into that now. But this, so if you look at it over here, nabla E also, so this implies nabla E, but this also can be viewed, well, it's just inherited from nabla P. Okay, as long as it's compatible with it, if covariant. If it's covariant, then we can, which is our assumptions, then we'll extend, it will restrict to this invariant subspace. Okay, so now just to finish up, then what we can do is we can just infinitesimalize this data here for our universe. So what we'll think of as spin connection is this data on the deformed algebra, and this will give us our associated connections as well. And I just want to analyze this. We fix a preferred deformation. So these formulae are slightly different from what we had before, in that that it's not exactly at the Poisson level. I'm fixing a preferred deformation. I don't know exactly how to get rid of that, but it's a reasonable deformation, which is just that we have well, of course, A times B star B. That's okay. That's the usual thing. Is AB plus lambda over 2 AB plus O of lambda squared. So okay, this is a preferred deformation. A dot eta is going to be A eta plus lambda over 2 nabla hat dA eta plus O of lambda squared. And A eta dot A is going to be A eta minus, maybe I should make these dots a bit bigger, minus lambda over 2 nabla hat dA eta. So now the proposition is that plus order lambda squared. And so now the theorem is that, so the lemma is that, so nabla dot of the form nabla dot p, so constructing this data at the deformed level, of the form nabla p, so the classical spin connection, plus lambda over 2 gamma of p plus O of lambda squared, obeys the above at order lambda. We get a deformation of the quantum differential calculus at order lambda. If and only if, well, what we need is a condition gamma, this gamma from C infinity of x to omega 1 horizontal obeys gamma of AP should be A gamma of P plus nabla hat x dA nabla p p minus nabla hat x dp dA minus nabla p ap. So then we have to solve these conditions. So this is the semi-classical data for a quantum, for a spin connection on a quantum principal bundle at semi-classical order. And when we start proving things about it, we'll need all the assumptions of a quantum principal bundle. That's where I'm going to end. So I just need to make one remark, is that at the classical level, so usual spin connection omega would be of the form omega I tensor EI, where EI a basis of G, of G star, no, G, sorry, and omega I's are in omega 1 of X, such that so the translation, the properties that we're familiar with would be this. This is the equivariance. And this is horizontality. Not horizontality exactly, but the condition we need for a connection on a principal bundle. So this is just writing out the conditions explicitly for a usual connection on a principal bundle. And then this, and more generally, we can consider omega bullet to be omega classical plus an order lambda 2 part alpha I tensor EI plus O of lambda squared. And here we need alpha I horizontal, and we need an equivariant. Alpha I plus alpha I. Okay, so that's going to be, so we can have a little bit more data than purely classical. We don't have to, but we can have a non-zero alpha here. So the theorem, which is where I'm going to end, is that if X is a Poisson principal bundle, omega a classical spin connection. So I could have written here, I could have said that, well, so there, I won't repeat. There's a corresponding, this gives you a corresponding nabla p. This omega gives you corresponding nabla p at the classical level. Spin connection omega with corresponding nabla p. Then gamma of p, and I'm going to define this as, and this is given by this formula, EI tilde applied to, so it's kind of Laplacian to EI, so this is kind of a Laplacian acting of P, acting on the function P, omega I, minus nabla hat X d EI tilde of P omega I minus EI tilde of P alpha I obeys is the required data, semi-classical data for nabla P bullet, and its equivariant, nabla P C acting on it is gamma of C acting on P. It's equivariant. So it obeys everything that we want. So this gives you data nabla E bullet at semi-classical at order lambda also. So you can compute this for the monopole connection, for the Q monopole connection at semi-classical order. It's not too exciting for that one, but you can compute it for other quantum homogeneous spaces, and it hasn't yet been done. Okay, so I'm going to stop there. In principle, this can be computed. So Yeah, but the proof, I just want to say the proof uses the main theorems. So nabla G hat bicovariant, the theorem that characterized it, the theorem that characterized this guy to be bicovariant, and the transversality condition. In fact, it uses all the conditions of a Poisson principal bundle. So this kind of shows that the whole theory hangs together well. And that's pretty much where the paper ended and where I'm going to stop. Okay. Thank you. So happy to take questions.
Yeah, so are there any questions? Okay, well, if not, I will start with a question. So Shahn, the results that you gave a couple of slides up with Edwin, where you were using
the construction on a quantum principal bundle of a bimodule connection on P. Yep.
So just to be clear, there were no Poisson assumptions there. This is for a general quantum.
No, this was here. I began by recalling the quantum group theory. So up to this point in this section, I started with a quantum principal bundle. This is all quantum, and then So at this point it's all quantum. So it's an arbitrary quantum principal bundle.
Oh, that's actually fantastic. So we have a large collection of these quantum principal bundles.
Yeah.
We were trying to show that they were bimodule connections, but failed completely. So if there's general results, that is great, actually. And this is
it's a kind of universal one, but it's not. If I pick a bimodule, it depends on how I can. So when I look at the associated bundle, I'm interested really in E tensor, in the associated bundle.
Yeah, sure.
And then you've got to ask, what is the bimodule? So the associated bundle is P tensor V invariance, right? It's this. Right. This is E, the associated bundle, and so then you've got to say what is the so this bimodule connection would imply a bimodule connection on E with where this commutes with V. So it's just the bimodule structure of P itself. So that's a natural example, but it's not the only example. I mean, you could imagine other bimodules which weren't constructed differently, to which this wouldn't apply. But this gives you a natural class of examples.
Okay, so just under the assumption that the right action on V is the trivial one.
Well, it's the one that comes from the bimodule structure on P.
Yeah.
It meets with V, if you like, which is the natural thing to do. But certainly we can, in the book, we looked at slightly more generally. But the one that's inherited from this connection up here, they automatically would be bimodule connections with that property.
And is it possible to write out the bimodule map, the flip?
Yeah. Well, it's constructed. It's constructed in its construction. It's in my notes. In fact, I can just add it in. Certainly. Actually, the well, let me just find it from the paper. It's certainly in there. But what it is it looks very innocent until you unpack what it actually entails. So there's a formula for it in the paper. So there's actually a formula for, if you want to know what sigma p is at this point, sigma p of p tensor, let's say dA, should be enough. This is pdA minus p0, the commutator of a omega over pi epsilon p1, like that. So that's an explicit formula, and so this lives in omega 1p. So then this is then the commutator of the functions on the base with functions on p, if you want. And here the zeros and ones are the coaction. It's the same data which goes into the connection, which into pi, that same data, but it enters like that. So that's the formula.
Okay, great. Okay, well, we'll look that up in the book.
Mm-hmm. So I should just say that this whole field, I mean, apart from me and my student Liam, I think no one's really. I mean, this is all relatively new stuff, so it hasn't yet been explored fully. The example that we have of the Q monopole, that has the fiber Hopf algebra has a zero Poisson bracket. It has a non-zero nabla hat. It has a non-zero contravariant connection. So this example that I showed you, the Q sphere, this is a non-commutative calculus. So it's a non-trivial nabla hat, but the Poisson bracket itself is zero. But if you looked at more interesting quantum principal bundles, for example, the instanton bundle or things like that, with the quantum SU2 fiber here, then it would start to get more interesting. And so when you compute the associated monopole bundle connection, it's in the paper, it doesn't look that different from the usual one. It has an extra factor, has a few extra terms in, but it's not too exciting. And that's because of this. But I think it would be more interesting to compute it for more interesting examples. But these Poisson brackets, you know, they wouldn't be easily discovered. I mean, it is true that Podlej classified sort of quantum SU2 or Poisson-Lie covariant Poisson brackets on the Poisson-Lie group SU2. So therefore, this is buried in Podlej's classification, but this is, you know, it's very general. But I just say that it hasn't really been computed very much. And also one could look at frame bundles and other things like that. So all of that hasn't been done at the Poisson level. Okay.
Okay, thank you. So are there any other questions? Hopefully I'm not. Just feel free to come in. There's no need to raise your hands. If not, is this so? But then when you go to higher orders as well, then there's going to be some.
Oh yeah, that's a very good question. So yeah, so I mean, what's really nice is that you have a self-contained theory, which, you know, I don't know if you've ever heard me talk or Edwin talk about Poisson-Riemannian geometry, but you can also semi-classicalize quantum Riemannian geometry. That doesn't involve principal bundles. That's a different direction. That involves connections with metrics, etc., with quantum metrics. But it involves omega-1. So you've got a Poisson contravariant connection for the calculus, and you've got a quantum metric and various conditions. And so that whole theory gives you a kind of window into quantum gravity at semi-classical order. If lambda was the Planck constant, not the Planck's constant, Planck's scale, then order lambda is not classical gravity. It's semi-quantum gravity. It bears the same relation to quantum gravity as classical mechanics bears to quantum mechanics, but it gives you non-trivial phenomenology. Non-trivial. So there's a whole paradigm for doing quantum gravity at order lambda in the Planck scale. And if you think about it, it's all you're ever going to measure anyway. You're never going to get to order lambda squared. So therefore, I think it's a nice self-contained paradigm by itself. Now, if you were to try to extend that theory and this theory to order lambda squared, you could assume the connection is flat and go for everything associative, but you wouldn't have many examples. And so the real thing to do is to work with non-associative geometry. But then you've got to say, well, what kind of non-associativity am I going to allow? And so then it starts getting very hairy. You can go to, you know, you can speculate that you can go to L infinity, or A infinity algebra and things like this, but you need something weaker than ordinary associativity. And so it's just, so, you know, no one has looked at this, so one should look at order 2 for this theory and the Poisson theory and see what kind of order 2 operatic theory you obtain. And whether it will fit with current ideas in higher geometry, I have no idea. But that's what you would need to do patiently. And in the meantime, there is a class of examples one could invent by twisting. So if you start with an associative quantum geometry and everything is covariant under a quantum group, then you can twist the quantum group by a cochain. And that will turn the quantum group into a quasi-Hopf algebra. Everything will start becoming, and it will twist the algebra into an associative algebra in the non-trivially associated category of the quasi-Hopf algebra modules. And so in that control setting, that setting of twisting, you can explore non-associative geometry. So there are examples where you can begin to do this and see everything works. But the downside of that is that because they're all obtained by twisting of the original geometry, they tend not to be that interesting. You can just untwist everything. All the formulae are basically twists of the usual formulae, and invariants tend to be invariant. So I think that's just a very, but it could give you insight into order 2 to what it might look like. Okay, so the book with Edwin Beggs for the Riemannian aspects ends, the last chapter has a section on this. I think it's a good direction for the future for those who like higher category theory.
Okay, good, thank you. So again, maybe there are no questions and no more questions. At that point, quickly, I'd like to thank Shahn again for a very nice talk. So coming up on the screen is the announcement for next week's talk. This is by Anshu from the Indian Institute of Science. So could you go back 1 second? From the Indian Institute of Science in Bhopal, and Sugato Mukhopadhyay at the Indian Statistical Institute. And Anshu's talk is homotopical stable ranks of C-star algebras. And Sugato was talking about Levi-Civita connections on bicovariant differential calculus. So the second talk a little bit closer to the spirit of today's talk. Okay, so hopefully we'll see some of you there next week. And yeah, thank you for coming.